The universe did not whisper its secrets to us. It shocked us into silence. For decades, astronomers believed they had a reliable timeline for how the cosmos grew up. The Big Bang ignited space and time. Darkness followed. Then slowly, patiently, the first stars flickered into existence. Galaxies assembled piece by piece over hundreds of millions of years. Black holes grew gradually, fed by the deaths of stars. This was the story written into textbooks, simulations, and confidence. And then James Webb opened its eyes. When the James Webb Space Telescope was launched, it was not introduced as a revolutionary threat to cosmology. It was presented as a successor, a refinement, a more sensitive instrument to confirm what scientists already believed, not to dismantle it. Webb was expected to sharpen the picture, not redraw it. Its mission sounded almost conservative. Look deeper. Look clearer. Look further back. Fill in the missing details of a universe we thought we already understood. But from the very first deep field images, something felt wrong, not broken, not noisy. Wrong in a more unsettling way. The universe was too bright, too structured, too mature. Galaxies appeared where none should exist. Stars burned intensely where theory predicted only darkness. Black holes loomed enormous when the universe itself was still a child. This was not a subtle discrepancy. It was a contradiction. Astronomy is a science built on patience. Light from distant objects takes time to reach us, sometimes billions of years. To look far away is to look back in time. The deeper we see into space, the closer we get to the beginning of everything. For decades, our view of the early universe was blurred and incomplete. We relied on indirect signals, statistical patterns, and computer simulations. Hubble gave us hints, shadows, outlines. James Webb was designed to deliver clarity. Webb sees the universe in infrared light, wavelengths stretched by the expansion of space itself. As the universe grows, light traveling through it is pulled longer and redder. The earliest galaxies are invisible to ordinary telescopes because their light has been stretched beyond visible wavelengths. Webb was built specifically to capture that ancient glow. In doing so, it became something more than a telescope. It became a time machine. And when that machine turned on, it delivered an uncomfortable truth. The early universe was not slow. It was not hesitant. It did not stumble its way toward complexity. It exploded into it. The first images showed galaxies that were massive, luminous, and densely packed with stars less than 1 billion years after the Big Bang. According to established models, such galaxies should not exist yet. There simply should not have been enough time. Stars take time to form. Heavy elements take time to accumulate. Gravity takes time to gather matter into large structures. And yet, there they were, fully formed, blazing. This was not a single anomaly. It was a pattern. Observation after observation repeated the same message. The universe grew up too fast. For scientists, this posed a dilemma. Either the observations were wrong or the models were incomplete. But the data was consistent, precise, and independently verified. James Webb was performing exactly as designed. It was not exaggerating, it was revealing. To understand why this is so disruptive, it helps to remember how fragile our cosmological models really are. They are not direct recordings of history. They are reconstructions, carefully balanced frameworks built from limited evidence: dark matter, dark energy, inflation, feedback mechanisms. Each component fits together like a delicate machine. Change one piece, and the whole system behaves differently. Webb did not gently nudge that machine. It struck it with force. Astronomers expected the early universe to be chaotic. Turbulent clouds of gas, small, irregular proto-galaxies, stars forming inefficiently, struggling against intense radiation and unstable conditions. Instead, they saw order, structure, efficiency, galaxies forming stars at astonishing rates, black holes already millions or billions of times more massive than the Sun. This forced an uncomfortable realization. Maybe the early universe was better at making structure than we thought. Maybe gravity worked faster. Maybe gas cooled more efficiently. Maybe dark matter clumped earlier and more aggressively. Or maybe something even more radical is missing from our understanding. Science advances not by comfort, but by contradiction. And James Webb delivered contradictions in abundance. The shock was not limited to distant galaxies. It extended to stellar behavior itself. Early stars, once assumed to be exotic and unstable, appeared to behave in familiar ways. They formed in clusters. They lived fast and died violently. Supernovae occurred much earlier than expected, enriching the surrounding space with heavier elements. This chemical maturity explains some of the unexpected brightness, but not all of it. Even more unsettling were the black holes. Supermassive black holes were discovered at epochs when the universe should barely have had time to form ordinary stars. Their existence implies either impossibly fast growth rates or a different origin entirely. This opened the door to ideas once considered fringe: direct collapse black holes, primordial black holes. Objects formed not from dying stars, but from the raw density of the early universe itself. If these ideas are correct, then black holes may not be late-stage products of cosmic evolution. They may be foundational architects rather than consequences. And this changes everything, because black holes influence galaxy formation, they regulate star birth, they shape the flow of gas. If massive black holes existed from the beginning, then galaxies may have grown around them, not the other way round. The timeline reverses. Cause becomes effect. The phrase, "the universe grew up too fast," is not a metaphor. It is a statement of scientific tension. Our equations predict one childhood. James Webb shows us another. This does not mean science has failed. It means science is doing exactly what it is supposed to do, confronting reality, even when it contradicts expectation. The early universe revealed by Webb is not hostile to understanding. It is inviting deeper questions. Why was matter so efficient at forming stars? Why did structure emerge so quickly? Why does the universe seem so eager to organize itself? Some answers may lie in physics we have not yet fully explored. The nature of dark matter, the behavior of gravity under extreme conditions, the role of radiation feedback in early environments. Others may require entirely new frameworks, adjustments to inflation theory, revisions to star formation efficiency, or new interpretations of cosmic expansion itself. What makes this moment extraordinary is not just the discoveries, but their timing. For the first time in human history, we are directly observing the era when the universe was less than 1 billion years old. Not inferring it, not modeling it, seeing it. This is the cosmic equivalent of finding childhood photographs that do not resemble the adult you thought you knew. the implications extend far beyond astronomy. They touch philosophy, origin stories, the nature of order in a universe born from chaos. If complexity emerges faster than expected, then perhaps the universe is predisposed toward structure, toward stars, toward planets, perhaps even toward life. But those conclusions must wait. Science moves carefully, even when surprised. James Webb has not rewritten the story yet. It has torn out the first draft and covered the margins with questions. What is clear is this: the early universe was not a quiet place waiting patiently for complexity to arrive. It was active, aggressive, creative. It built galaxies, stars, and black holes at a pace that defies our expectations. The shock of James Webb is not that it found something strange, it is that it found something familiar too early. Galaxies that look grown up, stars that behave like modern ones, structures that suggest maturity where infancy was assumed. This forces us to reconsider not just when things happened, but how. And that is where this story truly begins. Because if the universe grew up too fast, then we must ask what forces guided that growth, what unseen mechanisms accelerated it, and what else we may have misunderstood about our cosmic origins. James Webb did not give us comfort. It gave us clarity, and clarity, in science, is often the most disruptive force of all. Before James Webb ever opened its golden mirror to the sky, cosmology rested on a story that felt complete, not perfect, but coherent. A story built carefully over nearly a century, refined by observation, mathematics, and simulation. It was a model that explained the universe from its first fractions of a second to the vast cosmic web we see today. This was the universe we thought we understood. It began with the Big Bang, not an explosion in space, but an expansion of space itself. Around 13.8 billion years ago, all matter, energy, space, and time emerged from an extremely hot, dense state. In the first moments, the universe was simple. No atoms, no stars, no galaxies, only fundamental particles and radiation locked in a violent equilibrium. As the universe expanded and cooled, protons and neutrons formed, then hydrogen and helium. Light could finally travel freely, leaving behind the cosmic microwave background, a faint afterglow that still surrounds us today. This radiation became the earliest snapshot of the universe, a baby picture imprinted across the sky. After that came what astronomers called the cosmic dark ages. There were no stars yet, no galaxies, just vast clouds of neutral hydrogen slowly responding to gravity. This era was expected to last hundreds of millions of years. Gravity, though powerful, works patiently on cosmic scales. According to standard cosmology, the first stars formed around 100 to 200 million years after the Big Bang. These stars were thought to be massive, short-lived, and chemically simple, composed almost entirely of hydrogen and helium. They burned fast and died young, seeding the universe with heavier elements through their explosive deaths. Galaxies, in this model, formed slowly. Small clumps of matter merged into larger ones. Dwarf galaxies came first, then gradually assembled into spirals and ellipticals. Brightness increased over time as more stars formed. Structure emerged step by step, governed by gravity and limited by the availability of cool gas. At the heart of this story was dark matter, invisible, mysterious, and essential. Dark matter does not emit or absorb light, but it exerts gravity. It formed the scaffolding of the universe. halos of dark matter gathered first, pulling ordinary matter into their gravitational wells. Without dark matter, galaxies could not form the way they do. Then there was dark energy, an even stranger component responsible for the accelerating expansion of the universe. While dark matter pulls things together, dark energy pushes space apart. Together, these two unseen forces dominate the universe, shaping its past and future. This framework became known as the Standard Model of Cosmology, sometimes called Lambda CDM. Lambda represents dark energy. CDM stands for cold dark matter. It was not elegant in a philosophical sense, but it worked. It matched observations. It predicted large-scale structure. It explained the cosmic microwave background with remarkable precision. Within this model, time mattered. Growth was limited. Stars could not form instantly. Black holes could not appear fully grown. Everything had a schedule. Supermassive black holes, for example, were expected to grow slowly. They began as remnants of massive stars. Then they fed on surrounding gas and stars over billions of years. Even under optimistic assumptions, reaching billions of solar masses required time, a lot of it. Galaxies followed similar rules. Star formation efficiency was constrained by radiation pressure, supernova feedback, and gas cooling rates. Too much energy would blow gas away, slowing further star birth. Balance was essential. This slow, regulated growth was not just a preference, it was a necessity imposed by physics as we understood it. Computer simulations reinforced this view. Massive supercomputers modeled the universe from its earliest moments to the present day. They produced cosmic webs, filaments, voids, and galaxy clusters that closely resembled what telescopes observed. Confidence grew. The broad story seemed settled. Of course, there were open questions. The exact nature of dark matter, the cause of inflation, the origin of dark energy. But these were seen as details, not foundations. The timeline itself appeared robust. Then James Webb arrived. What made the shock so profound was not that Webb revealed something entirely alien, it was that it revealed something familiar far too early. Galaxies that looked like products of billions of years of evolution appeared when the universe was only a few 100 million years old. Within the old framework, such objects were statistical outliers at best. One or two might be explained away, but dozens, hundreds, appearing consistently across deep fields could not be ignored. This forced astronomers to confront a difficult possibility. Maybe the universe did not follow the gentle curve of growth they had mapped out. Maybe the early universe operated under different rules. This does not mean the standard model is useless. Far from it. It still explains the large-scale universe with remarkable success. The cosmic microwave background remains one of the greatest triumphs of predictive science. Galaxy clustering still follows dark matter distributions. Expansion measurements still align with theory. But cosmology has always depended on extrapolation. We take what we see nearby and extend it backward in time. James Webb has now given us direct access to that early era. And it is telling us that extrapolation may have limits. One possibility is that star formation was far more efficient in the early universe. Gas may have cooled faster. Radiation feedback may have been less effective at suppressing collapse. Metal-free environments may have allowed massive stars to form more easily. Another possibility is that dark matter behaved differently at early times. Perhaps it clumped faster. Perhaps small-scale structures formed earlier than simulations predicted. Slight changes in dark matter properties could dramatically alter early growth rates. There is also the possibility that black holes formed differently. If some black holes did not begin as stellar remnants, but instead formed directly from collapsing gas clouds, then the timeline shifts dramatically. Growth no longer starts from tiny seeds. It starts from giants. These ideas were once considered extreme. Now they are actively discussed. What James Webb has done is expose the assumptions hidden inside our models. Assumptions about efficiency, assumptions about feedback, assumptions about initial conditions. When observations violate those assumptions, the models must adapt. This is not a crisis. It is a recalibration. Science advances through tension between theory and observation. When they agree, progress slows. When they disagree, revolutions begin. The early universe revealed by Webb sits squarely in that productive tension. The universe we thought we understood was built on patience. The universe we now observe appears impatient. It rushed toward complexity. It assembled structure with surprising speed. It wasted no time in lighting up the darkness. This does not mean the old story was wrong. It means it was incomplete. And incompleteness is not failure. It is an invitation to look deeper, to refine, to rethink. Because understanding the early universe is not just about the past, it shapes everything that follows: galaxy evolution, black hole growth, planet formation, even the conditions that eventually allow life to emerge. If the universe learned how to build fast, then perhaps it learned other lessons early as well. James Webb did not erase our understanding. It exposed its edges. And in those edges, a deeper truth is waiting to be uncovered. When astronomers spoke about the cosmic dawn, they spoke cautiously. This was the era when the first light returned to the universe after the long darkness that followed the Big Bang. It was expected to be faint, fragile, and chaotic. Not a dramatic sunrise, but a slow and uncertain glow. For decades, this image shaped how scientists imagined the universe's earliest chapter. After the cosmic microwave background faded, the universe entered the dark ages. Space was filled with neutral hydrogen gas. No stars burned, no galaxies shone. Gravity was the only architect at work, quietly pulling matter into denser regions. This period was believed to last hundreds of millions of years, long enough for the universe to cool and settle. In theoretical models, the first stars were rare and extreme. Known as population 3 stars, they were thought to be enormous, sometimes hundreds of times more massive than the Sun. Without heavier elements to regulate their growth, gas clouds collapsed quickly, producing stars that burned intensely and briefly. Their lives may have lasted only a few million years before ending in violent supernovae or direct collapse into black holes. These first stars were not expected to form in large numbers. Conditions were harsh. Radiation from early stars would heat surrounding gas, preventing further collapse. Feedback was strong. Star formation efficiency was low. The universe, in this view, struggled to ignite. Galaxies, then, were expected to emerge slowly from these beginnings. Small clumps of stars formed primitive proto-galaxies. These structures were irregular, dim, and unstable. Over time, they merged, collided, and gradually assembled into larger systems. Order emerged from chaos, but only after long periods of interaction and growth. The earliest galaxies were predicted to be faint. Detecting them required pushing telescopes to their absolute limits. Astronomers expected only a handful to be visible at extreme distances. Most would remain hidden beyond our reach. Reionization was another key concept tied to cosmic dawn. As the first stars and galaxies formed, their ultraviolet light ionized surrounding hydrogen, transforming the universe from opaque to transparent. This process was thought to be slow and patchy, taking hundreds of millions of years to complete. The universe did not flip a switch. It gradually cleared its fog. Within this framework, timelines were tight. Everything depended on small differences accumulating over vast stretches of time. Tiny fluctuations in density, imprinted during inflation, grew under gravity. But growth was limited. The universe expanded rapidly, stretching matter apart even as gravity tried to pull it together. This balance between expansion and collapse defined the early universe. Too fast an expansion, and nothing would form. Too much collapse, and everything would clump too quickly. Models place the universe delicately between these extremes. Because of this, astronomers believed the first billion years would be relatively quiet in terms of large-scale structure. Activity existed, but it was modest. Brightness was low. Complexity was limited. This expectation shaped observational strategies. Scientists planned to search for faint signals, subtle hints, statistical patterns. No one anticipated being overwhelmed by abundance. James Webb changed that. When Webb observed the earliest galaxies, it found not scarcity, but excess. Not faint smudges, but luminous objects. Not hesitant formation, but rapid assembly. Cosmic dawn was not a struggle. It was a boom. This forced a re-evaluation of population 3 stars themselves. If early stars formed more efficiently, perhaps they were not all massive and short-lived. Perhaps a broader range of stellar masses existed from the beginning. Perhaps star formation physics did not change as dramatically as once thought. The discovery of an early supernova supports this idea. A stellar explosion, occurring only a few 100 million years after the Big Bang, implies that stars formed, evolved, and died quickly, but also in sufficient numbers to be observed. This suggests that early stellar populations may have been more numerous and more familiar than predicted. Galaxy formation also appeared accelerated. Some early galaxies showed signs of rotation, structure, and chemical enrichment. These are features associated with maturity. They imply multiple generations of stars had already lived and died. This raises a fundamental question. If the universe was capable of building such complexity so quickly, then what limited it later on? Why did growth slow? Why did structure stabilize? One possibility is that the early universe benefited from conditions that no longer exist. Higher densities, more abundant gas, different radiation environments. Gravity may have had more leverage when everything was closer together. Another possibility is that feedback mechanisms were weaker than expected. Perhaps radiation and supernovae did not suppress star formation as efficiently in primordial environments. Gas may have recycled more quickly, sustaining rapid growth. There is also the role of mergers. Early galaxies were closer together. Collisions were more frequent. Mergers can trigger intense starbursts, rapidly increasing mass and brightness. The early universe may have been a violent place, rich in interactions. What James Webb has revealed is not just that cosmic dawn happened earlier, but that it was more productive. The universe did not simply flicker to life, it blazed. This changes how astronomers interpret reionization. If many luminous galaxies existed early, reionization may have progressed faster and more uniformly than thought. The fog may have lifted sooner. The universe may have become transparent earlier in its history. These revisions ripple outward. They affect how we calculate the age of early objects, how we interpret distant signals, how we model the growth of everything that follows. Cosmic dawn was once imagined as a hesitant beginning, a slow awakening. James Webb suggests it was more like a rapid ignition. The darkness did not linger. And if the first light arrived sooner and stronger than expected, then the story of the universe's early years must be rewritten, not as a quiet prelude, but as a decisive opening act. The early universe was not waiting to become complex, it was racing toward it. To understand why James Webb revealed a universe that appears older than it should be, it is necessary to understand how Webb sees the cosmos. This telescope does not simply look farther, it looks differently. Its vision is tuned to the ancient language of light that has been stretched, weakened, and transformed by billions of years of cosmic expansion. Light travels at a finite speed. When we observe distant objects, we are not seeing them as they are now, but as they were when the light left them. This simple fact turns astronomy into a historical science. The deeper we look into space, the further back in time we see. Distance is time. Depth is history. The universe is expanding. As space itself stretches, light traveling through it stretches as well, wavelengths lengthen. Colors shift toward red. This effect, known as redshift, is not caused by motion through space, but by the expansion of space itself. The more distant an object is, the more its light has been stretched. The earliest galaxies emitted light mostly in ultraviolet and visible wavelengths. By the time that light reaches us, it has been stretched into the infrared. This means that ordinary optical telescopes are blind to the earliest chapters of cosmic history. They simply cannot see what has been redshifted beyond their range. This is where James Webb differs fundamentally from its predecessors. While Hubble excelled in visible and near-infrared light, Webb was designed specifically to operate deep in the infrared. Its instruments are sensitive to faint, cold, ancient signals that no previous telescope could detect. Webb's large mirror, over 6 meters in diameter, collects more light than any space telescope before it. This allows it to see extremely faint objects. But equally important is its location. Positioned far from Earth, at a stable gravitational point, Webb is shielded from heat and interference. It operates at extremely low temperatures, essential for detecting infrared light. Because of this, Webb does not just peer through space, it peers through time. When astronomers pointed Webb at seemingly empty regions of sky, they expected to see darkness punctuated by a few distant smudges. Instead, they saw galaxies layered behind galaxies, stretching back to within a few 100 million years of the Big Bang. These deep-field images were not long exposures in the traditional sense. They were efficient, precise, and overwhelming. Thousands of galaxies appeared where only dozens were expected, each one a data point. Each one a challenge to existing timelines. The key to this time travel is redshift measurement. By analyzing how much a galaxy's light has been stretched, astronomers can estimate how far away it is and how long ago the light was emitted. Some of the galaxies detected by Webb showed redshifts corresponding to times when the universe was less than 500 million years old. What shocked scientists was not just the distance, it was the brightness. Brightness implies stars. Stars imply time. Many stars. A galaxy does not become luminous instantly. Stars must form. They must burn. In some cases, they must live and die multiple generations to enrich the galaxy with heavier elements. Seeing bright galaxies so early implies that this process began almost immediately after the Big Bang. Webb's infrared instruments also allow astronomers to study the composition of these galaxies. Spectral lines reveal the presence of elements like oxygen, carbon, and nitrogen. These elements are forged in stars. Their presence indicates that stellar life cycles were already underway. This is where the tension becomes unavoidable. If galaxies were already chemically enriched, then stars must have formed earlier than models predicted. If stars formed earlier, then the dark ages were shorter. If the dark ages were shorter, then the universe transitioned to complexity faster. Webb also revealed structure. Some early galaxies showed disks, some showed signs of rotation. These are not random clumps, they are organized systems. Organization takes time, or at least it was believed to. The phrase, looking deeper than ever before, is often used casually in astronomy. In this case, it is literal. Webb is seeing objects whose light began its journey when the universe itself was young, hot, and compact. This capability changes the nature of evidence. Before Webb, early universe studies relied heavily on indirect measurements, background radiation, statistical fluctuations, theoretical extrapolation. Now, astronomers can point to individual objects and say, "This existed then." This shifts debates from speculation to observation. It also exposes biases in earlier observations. Telescopes that could not see infrared light underestimated the number and brightness of early galaxies. Selection effects made the early universe appear emptier than it was. Webb corrected that illusion, but correction brings consequences. Once you see what was hidden, you cannot unsee it. Webb's role as a time machine has forced cosmology to confront its blind spots. The early universe was not poorly understood because it was simple. It was poorly understood because we lacked the right tools. Now that we have those tools, the picture is changing rapidly. And this is only the beginning. Webb has observed only a fraction of the sky. Each new deep field expands the sample, and each new observation tests whether these early findings are universal or exceptional. So far, the trend is consistent. Early galaxies are abundant. Early stars are efficient. Early structure is real. James Webb has not merely extended our vision, it has accelerated our understanding by billions of years. We are no longer guessing what the early universe looked like. We are seeing it. And what we see is a universe that wasted no time becoming complex. When the first data from James Webb began to circulate among astronomers, disbelief came before excitement. The images showed galaxies that should not exist. Not because they were strange or unfamiliar, but because they were too large, too bright, and too mature for the age of the universe in which they appeared. These objects were not supposed to be there. According to every major model of galaxy formation, the early universe should have been dominated by small, faint systems, proto-galaxies with limited star formation, fragile structures still assembling their mass. Anything large and luminous was expected to come much later, after hundreds of millions or even billions of years of mergers and growth. Yet James Webb revealed galaxies with stellar masses comparable to modern systems at a time when the universe was less than 1 billion years old. Some appeared just 300 to 500 million years after the Big Bang. In cosmic terms, this is infancy. The universe was barely learning to form stars, yet here were galaxies already shining intensely, packed with stars, and radiating enormous amounts of energy. This is why astronomers began calling them impossible galaxies. The word impossible does not mean they violate the laws of physics. It means they violate our expectations based on those laws. Something in the timeline was wrong. Brightness is the first clue. A bright galaxy contains many stars. Stars require gas. Gas must cool and collapse. This process takes time. Not just time, but favorable conditions repeated over generations. To produce a galaxy as luminous as those seen by Webb, star formation must have been extremely efficient. Gas must have collapsed rapidly. Feedback from radiation and supernovae must not have shut the process down. Everything had to go right, and it had to go right very quickly. Mass is the second clue. Some early galaxies observed by Webb contain billions of solar masses worth of stars. Accumulating that much mass requires sustained growth, either through rapid star formation, frequent mergers, or both. Mergers were expected in the early universe, but not at a rate sufficient to explain what is being seen. Simulations predicted growth, but not this much, not this fast. Structure is the third clue. Some of these galaxies show signs of organization, central concentrations, disks, symmetry. These are features associated with gravitational settling and angular momentum balance, processes that were assumed to require time. The combination of brightness, mass, and structure is what makes these galaxies so disruptive. Each feature alone might be explained. Together, they form a pattern that challenges the entire framework. Initially, some scientists suspected misinterpretation. Perhaps the galaxies were closer than they appeared. Perhaps their masses were overestimated. Perhaps unusual stellar populations made them appear brighter than they really were. These possibilities were tested carefully. Redshift measurements confirmed their distances. Spectral analysis supported their mass estimates. Alternative explanations could not fully resolve the discrepancy. The galaxies were real, and they were early.
One proposed explanation is that star formation in the early universe was fundamentally different. Gas densities were higher, temperatures were higher, the cosmic environment was more compressed.
Gravity may have had an advantage when everything was closer together. In such conditions, gas clouds could collapse more rapidly, forming stars at rates far exceeding those seen today. If star formation efficiency approached theoretical maximums, then galaxies could build mass quickly. Another idea focuses on dark matter halos. Dark matter forms the gravitational backbone of galaxies. If dark matter halos formed earlier, or were more concentrated than expected, they could have accelerated the accumulation of gas and stars. Slight changes in dark matter behavior at small scales could produce dramatic effects in early galaxy growth. This does not require abandoning dark matter itself, only refining its properties. There is also the possibility that feedback processes were weaker in the early universe. In modern galaxies, radiation from young stars and energy from supernovae push gas away, limiting further star formation. In primordial environments, this feedback may not have been as effective. Metal-poor gas behaves differently. Cooling processes change. Radiation interacts differently with simpler atoms. The early universe may have allowed gas to recycle faster, sustaining rapid star birth. Another possibility is that we are witnessing a selection effect in reverse. Instead of seeing rare outliers, James Webb may be revealing what was normal. Perhaps massive galaxies formed early, and our previous view was incomplete. If that is the case, then the universe's early years were far more productive than assumed. The cosmic dawn was not a tentative phase. It was an era of intense construction. This forces a reconsideration of how galaxies evolve over time. If many galaxies formed early and rapidly, then later cosmic history may be more about regulation and maintenance than growth. The universe may have front-loaded its structure. This idea is uncomfortable because it challenges decades of simulation work. Simulations are powerful, but they rely on assumptions, star formation recipes, feedback strengths, initial conditions. Tweak any of these, and outcomes change. James Webb is now providing the observational anchor that those simulations must match. Theory must bend toward reality, not the other way round. What makes the situation more intriguing is that these impossible galaxies are not rare exceptions. They appear across multiple deep fields. Their abundance suggests a widespread phenomenon. This raises a deeper question. If the universe was capable of building massive galaxies so quickly, why did it slow down later? What changed? One answer lies in expansion. As the universe expanded, matter spread out, densities dropped, star formation became less efficient, feedback became more effective, growth slowed. Another lies in exhaustion. Early galaxies may have burned through their gas rapidly. Once fuel was consumed or expelled, growth stalled. Later galaxies inherited a more regulated environment. In this view, the universe experienced a growth spurt, a rapid childhood followed by a more measured adulthood. The impossible galaxies are not errors. They are messages from that growth spurt. They tell us that the universe's capacity for organization was strongest when conditions were extreme, when densities were high, when everything was close together, when gravity could act decisively. This also has implications for black holes. Massive galaxies often host massive black holes. If galaxies formed early, black holes likely did too. This helps explain the presence of supermassive black holes at unexpectedly early times. Galaxies and black holes may have grown together from the beginning, feeding off the same reservoirs of gas. This interconnected growth further compresses the timeline. Everything happens earlier, faster, more efficiently. The discovery of impossible galaxies does not invalidate cosmology. It sharpens it. It reveals where our intuition failed and where physics must be re-examined. The universe did not wait politely for structure to form. It rushed, and in that rush, it built galaxies that now force us to rethink the opening chapters of cosmic history. The early universe was not empty. It was busy. Once the existence of massive early galaxies was accepted, a deeper and more troubling question emerged. Not just how these galaxies formed, but how they grew so fast. Size alone was shocking, but growth rate was the real problem. The universe was not simply producing galaxies early, it was producing them at a speed that seemed physically unreasonable. Galaxy growth is governed by limits. Gas must cool before it can collapse. Stars must form from that gas. Energy released by those stars pushes back against further collapse. Supernovae inject turbulence. Radiation heats surrounding material. These processes act as brakes, preventing runaway growth. This balance is why galaxies today grow slowly and predictably. Yet James Webb's observations suggest that these brakes either failed or were far weaker in the early universe. Some galaxies appear to have formed stars at rates 10 to 100 times faster than modern galaxies of similar mass. In extreme cases, entire stellar populations may have assembled in a few tens of millions of years. On cosmic timescales, that is almost instantaneous. This level of efficiency forces astronomers to rethink the physics of early star formation. One factor is density. The early universe was denser than it is today. Matter was packed into a smaller volume of space. Gravity had more leverage. Gas clouds were closer together, making collapse easier and faster. High-density environments also increase collision rates. Clouds merge, shocks compress gas. Compression accelerates cooling, allowing stars to form rapidly. The early universe may have been a pressure cooker, primed for efficient star birth. Temperature also plays a role. Paradoxically, higher background temperatures can sometimes enhance star formation by preventing gas from fragmenting into too many small clumps. Instead of forming many low-mass stars slowly, gas may collapse into fewer, more massive stars quickly, boosting luminosity. Metallicity is another key factor. Early gas was metal-poor. Metals help gas cool, but they also enable complex feedback processes without metals. Radiation interacts differently with gas. Feedback may have been less effective at stopping collapse. This means early galaxies may have converted gas into stars with minimal resistance. Another contributor is merger frequency. The early universe was crowded. Galaxies were closer together. Collisions were common. Mergers funnel gas toward galactic centers, triggering intense bursts of star formation. These starbursts can rapidly increase stellar mass and brightness. If mergers were frequent enough, galaxies could grow in fits and bursts rather than gradually. This would explain the presence of massive systems at very early times. Dark matter, again, plays a central role. Dark matter halos determine how much gas a galaxy can retain. If early halos were more concentrated, they could trap gas more effectively, sustaining rapid star formation despite feedback. Small changes in halo structure can lead to large differences in growth rate. Simulations may have underestimated this effect. There is also the possibility that our assumptions about feedback are wrong. Modern galaxies experience strong regulatory effects. Radiation pressure pushes gas out. Supernovae carve cavities. Black holes inject enormous energy. These processes limit growth. But in the early universe, conditions were different. Gas inflow rates were high. Fresh material constantly streamed in along cosmic filaments. Even if feedback expelled gas, it may have been quickly replaced. In this scenario, feedback does not shut down star formation, it merely stirs it.
Another radical idea is that star formation laws themselves change under extreme conditions. Relationships derived from nearby galaxies may not apply to primordial environments.
The early universe may operate under a different regime of physics. This would mean that applying modern star formation recipes to early galaxies leads to systematic underestimation of growth rates. The universe was not violating physics. We were misapplying it. The implications of rapid growth extend beyond galaxies. They directly affect black hole formation. Black holes feed on gas. Rapid gas inflow fuels rapid black hole growth. This helps explain how supermassive black holes appeared so early. Galaxies and black holes likely grew together, each accelerating the other. Intense star formation drives gas toward galactic centers. Black hole growth releases energy that shapes the galaxy. This feedback loop may have operated differently in the early universe, favoring rapid assembly. If this co-growth began earlier than expected, then the distinction between early and late cosmic evolution blurs. The universe may have established its basic structure quickly, then spent billions of years refining it. This idea challenges the traditional narrative of slow build-up. Instead of a long childhood, the universe experienced a rapid adolescence. But this raises a deeper question. Why did growth slow later? If early conditions allowed such efficiency, what changed? Expansion is part of the answer. As the universe expanded, densities dropped, gas became more diffuse, inflow rates declined, feedback became more effective. The environment shifted from construction to regulation. Energy also accumulated. As stars and black holes formed, they filled space with radiation and heat. This energy altered gas behavior, making collapse more difficult. In this view, the early universe represents a unique window, a brief period when conditions aligned to maximize growth. Once that window closed, the universe entered a more stable, controlled phase. James Webb is showing us that this window was far more productive than expected. The challenge now is to quantify this productivity. How common were these rapid growers? How long did the growth spurts last? Were all early galaxies like this, or only a subset? Ongoing observations aim to answer these questions. Larger samples will reveal whether early rapid growth was universal or localized. Spectroscopy will clarify star formation histories. Simulations will be adjusted to match reality. What is already clear is that the early universe cannot be understood by simply scaling backward what we see today. It operated under different conditions, with different balances between forces. This realization has implications for everything that follows: galaxy evolution, black hole demographics, chemical enrichment, even the timing of planet formation. If galaxies built mass quickly, they produced heavy elements early. Those elements are the building blocks of planets. Planet formation may have begun sooner than previously thought. This does not mean life emerged early, but it shifts the timeline of possibility. Rapid galaxy growth is not just an astronomical curiosity, it reshapes the entire cosmic narrative. The universe did not take its time learning how to build. It learned quickly. And James Webb has revealed that learning curve in stark detail. The universe grew up too fast, not because it broke the rules, but because the rules were different when everything began. And understanding those differences is now one of the most important challenges in modern cosmology. For a long time, astronomers believed that the first stars were fundamentally different from the ones we see today. These earliest stars were imagined as extreme objects shaped by an environment unlike anything that exists now. They were thought to be enormous, unstable, short-lived, and rare. They were not supposed to resemble modern stars in any meaningful way. James Webb has begun to challenge that assumption. The early universe was chemically simple. It contained mostly hydrogen and helium, with almost no heavier elements. Metals, in astronomical language, are produced inside stars and spread through space when stars die. Because no stars had lived and died yet, the first generation of stars formed from pristine gas. This led scientists to believe that early stars, often called population 3 stars, would behave very differently. Without metals to help gas cool and fragment, collapsing clouds were expected to form extremely massive stars. These stars would burn at incredible temperatures, shine intensely, and die quickly, often collapsing directly into black holes. This picture made sense on paper. Simulations supported it, but it also came with consequences. If early stars were too massive and too short-lived, they would be rare. Their light would be difficult to detect. Their contribution to early galaxy brightness would be limited. James Webb complicated that picture. Observations of early galaxies show levels of brightness and chemical enrichment that suggest sustained star formation, not just brief flashes from a few massive stars. Some early galaxies show spectral signatures indicating multiple generations of stars. This implies that star formation was not only rapid, but also continuous. Even more surprising is the apparent similarity between early stellar populations and later ones. While early stars certainly formed under different conditions, their collective behavior may not have been as alien as once thought. The discovery of an early supernova is a key piece of evidence. A supernova occurring within the first billion years of cosmic history indicates that stars formed, evolved, and exploded on very short timescales. But more importantly, it suggests that stars followed recognizable life cycles. Supernovae are not just explosions, they are chemical factories. They produce heavier elements like oxygen, carbon, and iron. These elements enrich surrounding gas, altering how subsequent generations of stars form. The presence of these elements in early galaxies tells us that stars were forming in sufficient numbers to rapidly transform their environment. This is not the signature of a sparse, exotic population. It is the signature of active stellar ecosystems. This forces a reconsideration of population 3 stars. They may have existed, but perhaps they were not the only players. Perhaps star formation transitioned quickly from metal-free to metal-enriched modes. Perhaps the era of truly exotic stars was brief. If that is the case, then early star formation may have looked more familiar than expected. Intense, chaotic, but governed by the same basic physics that shapes stars today. This has major implications for galaxy growth. Stars are the engines of galaxies. Their radiation, winds, and explosions shape galactic structure. If stars behaved in familiar ways early on, then galaxies could stabilize and organize more quickly. It also affects reionization. Early stars emit ultraviolet light that ionizes hydrogen, making the universe transparent. If star formation was widespread and sustained, reionization may have progressed faster and more uniformly than predicted. This helps explain why James Webb sees so many bright galaxies so early. The universe may have been filled with starlight much sooner than expected. Another implication concerns the initial mass function, the distribution of star masses at birth. Astronomers often assume that this distribution is roughly universal. If early stars followed a similar distribution, then galaxy evolution models need adjustment. Even small changes in the initial mass function can dramatically alter predictions of luminosity, chemical enrichment, and feedback. James Webb's observations suggest that assuming an extremely top-heavy early population may be incorrect. This does not mean early stars were identical to modern ones. Conditions were harsher, radiation backgrounds were stronger, the gas dynamics were different. But the basic processes of collapse, fusion, and death may have followed recognizable patterns. The early universe, in this view, was not experimenting blindly. It found an efficient way to make stars quickly and kept using it. This challenges the idea that complexity requires long periods of trial and error. The universe may have discovered stable structures early and built upon them. The implications extend to black holes. Massive stars are one pathway to black hole formation. If early stars formed efficiently and in large numbers, then black hole seeds would be abundant. This provides a natural explanation for the rapid appearance of black holes. It also influences planet formation timelines. Metals are required to form rocky planets. If stars enriched their surroundings early, then the ingredients for planets existed sooner. Planet formation could begin earlier than previously assumed. This does not imply that habitable worlds existed early. Radiation levels were extreme, environments were unstable, but it shifts the earliest possible window. James Webb's view of early stars suggests continuity rather than rupture. The universe did not invent entirely new rules for star formation and then abandon them. It adapted familiar processes to extreme conditions. This continuity makes the early universe more understandable but also more unsettling. If familiar physics produced such rapid growth, then the limits we assumed may not be as strict as we thought. The early universe did not struggle to light its first stars. It ignited them efficiently, and once starlight appeared, it transformed everything around it. Galaxies brightened, gas chemistry changed, black holes fed, structure stabilized. Stars were not a late development in cosmic history. They were among the first architects. James Webb has shown us that the universe did not wait to become recognizable. It became familiar almost immediately. And that realization forces us to rethink how quickly complexity can emerge when the conditions are right. The first stars were not just the beginning, they were the acceleration. Among all the discoveries that James Webb has made about the early universe, few are as emotionally powerful or scientifically disruptive as the detection of the most distant supernova ever observed. A single star exploding nearly 13 billion years ago may seem insignificant against the scale of the cosmos, but this event carries enormous weight. It is a timestamp, a confirmation, a challenge written in light. A supernova is the death of a star. But more importantly, it is proof that the star lived first. To observe a supernova so early in cosmic history means that a star had time to form, burn its fuel, and reach the end of its life. This sequence takes millions of years even for the most massive stars. When placed so close to the beginning of the universe, those millions of years matter. The universe was only about 730 million years old when this explosion occurred. That leaves a narrow window. Stars had to form very early. They had to do so efficiently. And they had to reach maturity quickly enough to die violently. This immediately compresses the cosmic timeline. Before James Webb, supernovae from such early times were purely theoretical. Astronomers expected them to exist, but detecting one was considered extremely unlikely. The signals would be faint. The distance is enormous. The background noise overwhelming. Webb changed that equation. By operating in the infrared and observing repeatedly over time, Webb was able to detect a subtle brightening and fading in a distant galaxy. This change was not random. It followed the characteristic light curve of a supernova. A rapid rise in brightness, followed by a slower decline. This pattern is unmistakable. It is the signature of stellar death. The significance of this detection goes beyond the event itself. It confirms that early stars were not only forming, but evolving in recognizable ways. They lived lives governed by nuclear fusion, energy balance, and gravitational collapse. They died in explosions that resemble those we see in the nearby universe. This challenges the idea that early stars were so exotic that their deaths would be fundamentally different. Instead, it suggests continuity. The universe learned how to make stars early, and it learned how to end them too. Supernovae play a critical role in cosmic evolution. They are the primary source of heavy elements. Everything heavier than hydrogen and helium is forged inside stars and released during stellar deaths. Oxygen, carbon, silicon, iron. These elements are essential for planets, chemistry, and life. The detection of an early supernova implies that chemical enrichment began sooner than expected. The universe was not chemically pristine for long. Within a few 100 million years, stars were already seeding space with the building blocks of complexity. This helps explain why James Webb sees early galaxies with unexpectedly rich spectra. Metals should not exist yet, according to older models, but supernovae provide a mechanism. If stars formed early and died quickly, enrichment could happen rapidly. The presence of metals changes everything. Gas cooling becomes more efficient, star formation becomes easier, feedback mechanisms evolve, galaxies can grow faster and more stably. This creates a feedback loop. Early star formation leads to early supernovae. Supernovae enrich the environment. Enriched gas forms stars more efficiently. Galaxies brighten, growth accelerates. The early universe becomes a self-amplifying system. This single supernova also provides a test of stellar physics. Its light curve and spectral properties can be compared to models. So far, they appear consistent with known types of supernovae. This suggests that the fundamental processes governing stellar death were already in place. This consistency is both reassuring and unsettling. Reassuring because physics appears stable across cosmic time. Unsettling because it means the early universe did not need special rules to behave this way. Ordinary physics, under extreme conditions, produced extraordinary results. The detection also challenges assumptions about the rarity of early supernovae. If James Webb detected one in a limited field of view, it implies that many more exist. They may be common, not exceptional. This has implications for reionization. Supernovae inject energy into the intergalactic medium. They help clear gas. They contribute to heating and ionization. A universe filled with early supernovae would transition faster from darkness to transparency. It also affects black hole formation. Some massive stars collapse directly into black holes without exploding. Others explode and leave behind dense remnants. Both pathways produce black hole seeds. Early supernovae imply early seeds. These seeds can grow by accreting gas and merging with others. This helps explain the presence of supermassive black holes at early times. Once again, everything connects. The emotional power of this discovery lies in its intimacy. A supernova is a single event, a single star ending its life, yet it echoes across billions of years to reach our detectors. That light traveled through an expanding universe, past forming galaxies, through cosmic filaments, to reach a telescope built by a species that would not exist for another 13 billion years. That connection compresses time in a different way. It reminds us that cosmic history is not abstract. It is recorded in individual events. This supernova also serves as a reality check. Theories can be elegant, simulations can be impressive, but a single observation can overturn expectations. Astronomers now face new questions. How common were early supernovae? What types dominated? How did they influence early galaxy evolution? Did they regulate star formation or amplify it? Future observations will search for more. Repeated deep field monitoring will reveal transient events. Each detection will refine the timeline. James Webb has shown that the early universe was not static between the Big Bang and galaxy formation. It was dynamic. Stars lived and died. Explosions reshaped environments. Chemistry evolved. The idea of a long, quiet dark age is fading. Instead, the early universe appears active, noisy, and transformative. This also influences how we think about cosmic storytelling. Beginnings are often imagined as simple, clean, empty. James Webb suggests the opposite. The universe began messy, energetic, and productive. The first stars did not quietly fade into history. They exploded. And in doing so, they marked the universe with elements, energy, and momentum that shaped everything that followed. This supernova is not just the oldest one we have seen. It is a signal that the universe learned very early how to recycle matter, how to build complexity from destruction. Life, as we know it, depends on supernovae. The iron in blood, the calcium in bones, the oxygen we breathe, all forged in stellar deaths. To see such a death so close to the beginning of time is to realize how quickly the universe set the stage for everything else. The universe did not wait billions of years to begin its chemistry. It began almost immediately, and James Webb caught it in the act. This discovery does not close a chapter. It opens one. Because if stars were already dying this early, then the story of cosmic evolution must be retold with urgency. The universe was in a hurry, and its first explosions are now lighting the way back to its origins. If early stars rewrote the timeline, early black holes shattered it completely. Nothing in modern cosmology was prepared for what James Webb revealed at the centers of the earliest galaxies. Objects with masses millions to billions of times that of the Sun, already in place when the universe itself was barely out of infancy. Black holes were never expected to appear late in cosmic history, but they were expected to grow slowly. According to traditional theory, black holes begin as remnants of massive stars. When a large star exhausts its fuel, its core collapses, forming a black hole a few times the mass of the Sun. From there, growth is incremental. Gas falls in, stars are swallowed. Mergers occur. Over billions of years, a supermassive black hole slowly emerges. This process works well in the modern universe. It explains the black holes at the centers of nearby galaxies. It matches observed feeding rates. It fits within known physical limits. But it fails completely in the early universe. James Webb detected active black holes, quasars, and accreting monsters at epochs when there simply should not have been enough time for such growth. Some of these black holes already weighed hundreds of millions or even billions of solar masses less than a billion years after the Big Bang. To reach such sizes through normal growth would require accretion at or above theoretical maximum rates, sustained without interruption from the moment the first stars formed. Even then, the math barely works. And nature is rarely that cooperative. This creates a crisis of origin. Either black holes grew far faster than physics allows, or they did not start small. The observations point toward the second possibility. In the early universe, black holes appear not as gradual products of stellar death, but as fundamental structures present from the beginning of galaxy formation. They are not late arrivals. They are early anchors. James Webb's infrared sensitivity allowed astronomers to identify the spectral fingerprints of accreting black holes in young galaxies, emission lines broadened by extreme gravity, intense radiation from gas heated to millions of degrees. These are unmistakable signatures of active black holes. What makes this discovery so unsettling is how common these objects appear to be. Early galaxies do not just occasionally host massive black holes. Many of them do. This suggests that black hole formation was not a rare accident. It was a standard outcome. This realization forces a re-examination of black hole seed models. One possibility is direct collapse. Instead of forming from stars, some black holes may have formed when massive clouds of gas collapsed directly under their own gravity. In this scenario, Gas does not fragment into stars. It collapses as a whole, forming a black hole tens of thousands or even millions of times the mass of the Sun in a single event. This bypasses the slow growth problem entirely. Instead of starting small and growing painfully fast, black holes start large. Direct collapse requires special conditions. Gas must be dense, hot, and free of metals. Radiation must suppress star formation while allowing collapse. For a long time, these conditions were thought to be rare. James Webb suggests they may not have been. The early universe was filled with dense gas. Metals were scarce. Radiation fields were intense but uneven. Conditions may have aligned frequently enough to produce many massive black hole seeds. Another possibility is even more radical: primordial black holes. Primordial black holes are hypothetical objects formed not from stars or gas clouds, but directly from density fluctuations in the early universe. In the moments after the Big Bang, regions of space may have been dense enough to collapse into black holes immediately. If such objects formed, they would be as old as the universe itself. They would not require stars. They would not require time to grow. They would exist from the beginning. For decades, primordial black holes were considered speculative, interesting, but unsupported. James Webb's discoveries have brought them back into serious discussion. The existence of massive black holes at extreme redshifts does not prove primordial origins, but it makes them plausible. If even a small fraction of dark matter consists of primordial black holes, they could serve as seeds for galaxy formation. Gas would fall into their gravity wells, stars would form around them, galaxies would assemble with black holes already in place. This flips the traditional narrative. Galaxies do not create black holes. Black holes help create galaxies. The implications are profound. Black holes influence their surroundings through gravity and energy release. They regulate star formation. They shape galactic structure. If they existed early, they would accelerate organization. This could explain why galaxies appear so mature so quickly. They had anchors, centers of gravity, engines driving inflow and growth. The discovery of a runaway supermassive black hole, moving through space and creating a galaxy-sized bow shock, further underscores how dynamic and violent early black hole environments were. These objects were not passive. They interacted, merged, and reshaped their surroundings. This suggests that black hole mergers may have been common in the early universe. Mergers increase mass quickly. Two black holes combining instantly double their mass. Repeated mergers could rapidly build enormous objects. This again compresses the timeline. But mergers alone are not enough. Feeding is required. Gas must fall in. Early galaxies appear to have had abundant gas. Inflows along cosmic filaments could continuously supply black holes with fuel. In the modern universe, black hole feeding is often chaotic and intermittent. In the early universe, it may have been steady and intense. This raises questions about feedback. Black holes release enormous energy when they feed. This energy can heat gas and suppress star formation. Yet early galaxies seem to have sustained high star formation rates despite active black holes. This suggests that feedback mechanisms behave differently early on. Energy may have escaped more easily. Gas inflows may have overwhelmed feedback. The balance between suppression and growth may have favored growth. Once again, the early universe appears optimized for rapid assembly. The presence of early black holes also affects reionization. Accreting black holes emit powerful radiation. They contribute to ionizing hydrogen. If many existed early, they may have played a significant role in transforming the universe from opaque to transparent. This has been debated for years. James Webb provides new data to test these ideas. Another implication concerns gravitational waves. Mergers of massive black holes produce powerful ripples in space-time. If early black hole mergers were common, the universe may be filled with a background of gravitational waves originating from its first billion years. Future detectors may one day detect these signals, providing independent confirmation of early black hole activity. What James Webb has done is force cosmology to confront the possibility that black holes are not endpoints, but beginnings. They may be among the first complex objects the universe produced. This challenges intuition. Black holes are often associated with destruction, with endings, with death. Yet, in cosmic history, they may represent creation, structure, organization. This duality is unsettling and elegant at the same time. The early universe revealed by James Webb is not a place where black holes slowly emerge from stellar debris. It is a place where black holes appear as fundamental components, shaping everything around them from the start. This does not mean all questions are answered. Many remain open. How common were direct collapse events? Did primordial black holes exist? How did feedback operate? How did black holes and galaxies co-evolve? But one thing is clear. The early universe did not wait for black holes to catch up. They were already there, and their presence helps explain why the universe appears to have grown up too fast. Because when gravity has powerful anchors from the beginning, structure does not hesitate. It accelerates. Black holes were not late-stage consequences of cosmic evolution. They were among its earliest drivers, and James Webb has made it impossible to ignore them. Once the existence of massive black holes in the early universe was established, the debate shifted from disbelief to mechanics. If these objects were real, and the data strongly indicated they were, then the central question became unavoidable. How did supermassive black holes grow so fast? This problem is not philosophical, it is mathematical. Black hole growth is governed by well-understood physical limits. Matter falling into a black hole releases energy. That energy pushes outward, resisting further inflow. This creates a natural ceiling on how fast a black hole can feed. Astronomers call this the Eddington limit. At the Eddington limit, the outward pressure of radiation balances the inward pull of gravity. Feed faster than this, and the black hole chokes on its own energy output. Feed slower, and growth becomes inefficient. Even under ideal conditions, continuous feeding at the Eddington limit takes time. Starting from a stellar mass black hole, it would require hundreds of millions to over 1 billion years to reach supermassive scales. The early universe did not have that time. James Webb observed black holes with masses of hundreds of millions to billions of solar masses, when the universe itself was less than 1 billion years old. Some appear when the universe was only 500 million years old. The math does not work. To make it work, several assumptions must break. One possibility is that black holes fed above the Eddington limit for extended periods. This is known as super-Eddington accretion. Under certain conditions, geometry and radiation trapping can allow matter to fall in faster than expected. This can happen if gas forms a thick disk around the black hole. Radiation becomes trapped within the inflowing material. Instead of escaping outward, the pressure does not push back as effectively. As growth accelerates, super-Eddington accretion has been observed in limited cases in the modern universe. but sustaining it for hundreds of millions of years seems unlikely. The environment would need to be extraordinarily stable and gas-rich. The early universe may have provided such conditions. Gas was abundant, inflows along cosmic filaments were steady, turbulence may have helped funnel matter inward. But even optimistic models struggle to explain the most massive early black holes. Another possibility is that black holes did not grow continuously. Instead, they may have grown in bursts, periods of intense feeding followed by quieter phases. Mergers between black holes could also contribute, instantly increasing mass without accretion limits. Mergers are efficient. Two black holes collide and combine, producing a single more massive object in the crowded early universe. Mergers may have been frequent. Galaxies were close together. Interactions were common. Black holes would inevitably meet. Repeated mergers could rapidly build mass. But mergers alone are insufficient. The universe would still need to produce many initial black hole seeds to merge. This brings us back to the question of origin. If black holes started larger, the growth problem becomes easier. A seed of 100,000 solar masses requires far less time to reach 1 billion than a seed of 10 solar masses. This is why direct collapse models are so attractive. In these models, black holes form directly from massive gas clouds without passing through a stellar phase. The resulting black hole is already massive. Direct collapse requires very specific conditions. Gas must be dense and hot. Cooling must be suppressed to prevent fragmentation into stars. Radiation from nearby sources may help keep the gas warm while allowing collapse. For a long time, these conditions were assumed to be rare. James Webb's discoveries suggest they may have been more common. The early universe was a patchwork of radiation fields, gas densities, and temperature variations. Some regions may have naturally favored direct collapse. If even a small fraction of early halos produced massive black hole seeds, the growth problem eases dramatically. There is also the possibility that multiple mechanisms operated simultaneously. Some black holes formed from stars, others from direct collapse, still others from primordial origins. Growth pathways may have varied across environments. This diversity would produce a population of black holes with different histories but similar outcomes. By the time James Webb observes them, the details of their origins are hidden behind billions of years of growth. Another important factor is feedback. In the modern universe, black hole feedback is efficient at regulating growth. Jets and radiation heat surrounding gas, limiting further accretion. But early galaxies appear to have sustained both high star formation and active black holes simultaneously. This suggests that feedback was either weaker or less effective at shutting down inflow. One explanation is that gas inflow rates were simply too high. Even if feedback expelled gas locally, fresh material flowed in along filaments, the black hole could continue feeding. Another is that early black hole energy escaped more easily. Porous gas distributions may have allowed radiation to leak out without disrupting inflow. The geometry of early galaxies may have favored growth over regulation. This paints a picture of an early universe where growth dominated. Conditions favored accumulation rather than balance. The brakes that slow down growth today had not yet fully engaged. This also helps explain the tight correlation between black hole mass and galaxy properties observed in the modern universe. If black holes and galaxies grew together from the beginning, their masses would naturally track each other. This co-evolution implies coordination. Star formation feeds black holes. Black holes influence star formation. Both draw from the same gas reservoir. In the early universe, this loop may have been particularly efficient. The idea that supermassive black holes grew too fast is not just a technical problem. It challenges our intuition about how complexity arises. Black holes are extreme objects. They represent the densest concentrations of matter possible, yet the universe produced them quickly. This suggests that extreme outcomes may be natural under extreme conditions. James Webb is not showing us a universe that violated physics. It is showing us a universe that exploited it. Under high density, high inflow, and minimal regulation, gravity can act with ruthless efficiency. Matter falls inward. Structure forms rapidly. Mass accumulates. This efficiency fades as the universe expands and cools. Densities drop. Inflows weaken. Feedback strengthens. Growth slows. The universe transitions from a phase of rapid construction to one of long-term evolution. In this context, the early appearance of supermassive black holes is not anomalous, it is a consequence of timing. The universe built its heaviest structures when conditions were optimal. What makes James Webb's discoveries so powerful is that they force us to confront the limits of our models. Simulations tuned to match the modern universe may fail to capture early extremes. This does not mean simulations are wrong. It means they need recalibration, star formation recipes, feedback efficiencies, accretion physics. All must be revisited. Future observations will refine this picture. More early quasars, better mass estimates, detailed spectra. Each data point will narrow the range of possibilities. Gravitational wave astronomy will also play a role. Mergers of early black holes leave signatures that may one day be detected. These signals would provide direct evidence of early black hole growth pathways. For now, James Webb has delivered a clear message. Supermassive black holes did not slowly crawl into existence. They sprinted. Their growth was rapid, aggressive, and efficient. And understanding how they achieved this speed is essential to understanding why the universe itself appears to have grown up too fast. Because black holes are not just passengers in cosmic history. They are drivers. And the early universe gave them the road, the fuel, and the momentum to reach astonishing speeds. The story of early black hole growth is not about breaking limits. It is about discovering that the limits were different at the beginning. And James Webb has shown us exactly where those differences begin. As astronomers struggled to explain how black holes could appear so massive so early, attention turned toward an idea once considered speculative and controversial: primordial black holes. Objects that did not form from stars, gas clouds, or galaxies, but from the universe itself. Primordial black holes are fundamentally different from the black holes formed by stellar collapse. They would have formed in the first moments after the Big Bang, when the universe was hot, dense, and violently unstable. Tiny fluctuations in density could have been amplified by gravity, collapsing directly into black holes before stars or galaxies ever existed. In this scenario, black holes are not late products of cosmic evolution. They are among its first structures. For decades, primordial black holes existed mostly on the fringes of cosmology. They were mathematically possible but observationally unproven. Most versions of the theory suggested either very small black holes that evaporated quickly or objects too rare to matter. James Webb has reopened this discussion. The reason is not direct detection. Webb has not seen a primordial black hole forming. Instead, It has revealed consequences that are difficult to explain without something like them. The existence of supermassive black holes in the early universe creates a timing problem. Stellar collapse is too slow. Even direct gas collapse struggles to account for the most extreme cases. Primordial black holes offer a shortcut. They remove the need for growth entirely. If black holes already existed, with substantial mass shortly after the Big Bang, then everything else becomes easier to explain. Galaxies would naturally form around them. Gas would fall into their gravity wells. Stars would ignite in dense regions shaped by black hole gravity. This idea reverses the traditional sequence of cosmic evolution. Instead of galaxies creating black holes help create galaxies. One of the most intriguing possibilities is that primordial black holes could account for some or all of dark matter. Dark matter makes up most of the matter in the universe, yet its nature remains unknown. If even a fraction of dark matter consists of primordial black holes, their gravitational influence would be profound. They would seed structure formation. They would accelerate collapse. They would explain why galaxies appear earlier and more massive than expected. James Webb's discovery of early, massive, and numerous galaxies fits naturally into this picture. Primordial black holes embedded within dark matter halos could act as catalysts, pulling gas inward and triggering rapid star formation. This does not mean primordial black holes must be supermassive from birth. They could have formed with a wide range of masses. Smaller primordial black holes could merge, forming larger ones. Others could grow through accretion. The key difference is that growth begins from a head start. Another reason primordial black holes are being reconsidered is their potential to explain observational inconsistencies beyond galaxy formation. They could influence reionization. They could affect gravitational lensing. They could leave imprints in the cosmic microwave background. So far, none of these signals definitively confirm their existence, but James Webb's data has made it harder to dismiss them. The early universe revealed by Webb appears unusually efficient at building structure. Primordial black holes provide a mechanism for that efficiency without requiring new physics. Gravity alone is sufficient. There are, however, challenges. Primordial black holes cannot be too abundant or too massive, or they would disrupt observations we already understand. They must fit within tight constraints from gravitational lensing, background radiation, and galaxy dynamics. This means that if primordial black holes exist, they likely represent a partial solution, not the entire story. They may coexist with direct collapse, black holes, and stellar remnants. Cosmic history may not follow a single pathway. It may be layered, different mechanisms dominating in different environments. James Webb is revealing the outcomes of those mechanisms without yet revealing their full causes. It is showing us a universe that appears preceded with complexity. The philosophical implications are striking. If primordial black holes exist, then some of the universe's most extreme structures formed before stars, before galaxies, before light itself escaped freely. Gravity would have been shaping destiny from the very beginning. This challenges the idea that complexity emerges slowly from simplicity. Instead, complexity may have been present from the start, embedded in the initial conditions of the universe. It also reframes the question of cosmic inevitability. If black holes formed immediately, then large-scale structure may have been unavoidable. The universe may have been destined to organize itself rapidly. This does not diminish the role of chance. Density fluctuations were random. Not all regions would collapse. But it suggests that the universe had multiple pathways toward structure, not just one. Astronomers remain cautious. Extraordinary claims require extraordinary evidence. Primordial black holes remain hypothetical, but they are no longer fringe. James Webb has not confirmed their existence. It has done something arguably more important. It has made them plausible. Future observations may test this idea more directly. Gravitational wave detectors could reveal mergers of black holes with masses inconsistent with stellar origins. Precise measurements of galaxy distributions could reveal anomalies in dark matter behavior. Until then, primordial black holes remain a compelling solution to a growing problem. They offer an explanation for why the universe appears older than it should be, why black holes appear too massive too early, why galaxies seem to have grown up too fast. Whether they exist or not, their resurgence marks a turning point in cosmology. The early universe is no longer a simple place where structure emerged reluctantly. It is a place where gravity may have acted immediately, decisively, and creatively. James Webb has forced us to consider that the universe may have been born with seeds of complexity already in place. And if that is true, then the story of cosmic evolution is not just about growth, it is about inheritance. The universe did not start from nothing. It started with potential. And that potential may have taken the form of black holes born at the dawn of time. This idea remains unproven, but it can no longer be ignored, because the universe James Webb is revealing looks like one that had a head start, and primordial black holes may be the reason why. Among the most unexpected and visually striking discoveries linked to early black holes is the detection of a runaway supermassive black hole carving a structure on the scale of an entire galaxy. This was not a quiet object sitting at a galactic center. It was moving fast, and as it moved, it left behind a shockwave so large it rewrote assumptions about how black holes interact with their environments. The idea of a runaway black hole sounds dramatic, but it is grounded in well-understood physics. When galaxies merge, their central black holes do not immediately settle. They orbit each other. They interact gravitationally. And when they finally merge, the combined system can receive a powerful kick. This kick comes from gravitational waves. When two black holes collide, they release enormous energy in the form of ripples in space-time. If that energy is emitted unevenly, the resulting black hole recoils like a cannon firing backward. In extreme cases, this recoil can eject the black hole from the center of its host galaxy. For decades, this phenomenon existed mostly in simulations. Astronomers believed it could happen, but evidence was limited. James Webb provided that evidence. Webb detected a supermassive black hole racing through space, dragging gas along with it and compressing the surrounding medium into a massive bow shock. This shock front stretched tens of thousands of light years, comparable to the size of a galaxy. A bow shock forms when an object moves faster than the speed of sound through a medium. In this case, the medium was interstellar gas. The black hole's motion compressed the gas, heating it and triggering intense radiation. This observation reveals several important truths about the early universe. First, black hole mergers were already happening. Mergers require time, proximity, and abundance. Seeing a recoiling black hole implies that massive black holes existed, interacted, and merged early in cosmic history. Second, the environments around early black holes were rich in gas. Enough gas existed to form a visible, large-scale shock. This supports the idea that early galaxies were gas-dominated and dynamically active. Third, black holes were not passive residents of galaxies. They were mobile, disruptive, and influential beyond their immediate vicinity. The presence of a galaxy-sized bow shock means that a single black hole can reshape its environment over vast distances. Gas is compressed ahead of it, potentially triggering star formation. Behind it, gas is stripped away, altering the galaxy's structure. This paints a picture of the early universe as violent and kinetic. Galaxies collided, black holes merged, recoil events displaced massive objects, shock waves propagated through gas-rich environments. This violence may have played a role in rapid galaxy evolution. Compression from shocks can ignite starbursts. Displacement of black holes can redistribute energy. These processes could accelerate growth and restructuring. The runaway black hole also challenges assumptions about galaxy centers. In the modern universe, supermassive black holes are almost always found at galactic cores. This is often treated as a stable configuration. James Webb shows that stability may come later. In the early universe, centers were transient. Black holes could be ejected, wander, or oscillate before settling. This has implications for black hole demographics. Some galaxies may have temporarily lacked central black holes. Others may have hosted multiple. Some black holes may have roamed intergalactic space. Roaming black holes are difficult to detect, but they would still interact gravitationally with gas and stars. Their influence could extend beyond visible galaxies. This discovery also reinforces the idea that early black hole growth involved mergers as much as accretion. Mergers bypass feeding limits. They instantly increase mass. Frequent mergers would rapidly build supermassive objects. In a crowded early universe, such mergers would be common. Galaxies were closer together, interaction rates were higher, black holes had more opportunities to collide. The resulting gravitational wave signals would have filled the early universe. Today, those waves are stretched and weakened, forming a background hum of space-time distortion. Future gravitational wave observatories may detect this background, offering a new way to probe early black hole activity. James Webb provides the electromagnetic counterpart to that story. The runaway black hole also highlights the interconnectedness of cosmic processes. Black holes influence gas. Gas fuels stars. Stars shape galaxies. Galaxies merge, creating more black holes. This feedback loop operates across scales, from the subatomic to the galactic. What makes this discovery especially important is that it cannot be easily explained away. A galaxy-sized bow shock requires immense energy and motion. It is not a statistical fluke, it is a physical imprint. It tells us that black holes were dynamic agents from very early times. This challenges older models that treated black holes as slow-growing, centrally confined objects. Instead, they appear as active participants in shaping the cosmic landscape. The early universe was not a calm place where structures gently assembled. It was turbulent. Collisions were frequent. Energy flowed violently, and black holes were at the heart of that turbulence. This also influences how we think about feedback. Black hole feedback is often modeled as jets or radiation emanating from a fixed center. A moving black hole introduces a different kind of feedback: mechanical, directional, sweeping. Such feedback could carve channels in gas, redistribute matter, and alter star formation patterns across entire galaxies. The runaway black hole discovery suggests that feedback mechanisms in the early universe were more varied and more extreme than previously assumed. It also hints at why early galaxies evolved so quickly. Violent processes accelerate change. Calm systems evolve slowly. The early universe was anything but calm. James Webb has shown us that black holes were not just growing, they were moving. They were colliding. They were reshaping space on colossal scales. This reinforces the central theme emerging from all of Webb's discoveries. The universe did not develop gradually and politely. It evolved aggressively. Structures formed fast. Interactions were intense. Feedback was powerful. The runaway black hole is not an isolated curiosity. It is a symptom of a universe in motion. A universe where gravity acted decisively, not patiently, and where black holes were not the quiet endpoints of stellar evolution, but the engines driving cosmic transformation. The early universe was not static. It was alive with motion. And James Webb has captured one of its most dramatic expressions. As more James Webb observations accumulated, a subtle but profound pattern began to emerge. The early universe was not just active, it was organized. Structure did not appear reluctantly or gradually. It appeared early, coherently, and on large scales. This realization struck at the heart of how cosmologists understood cosmic evolution. For decades, the early universe was imagined as a turbulent, disordered environment. Matter clumped unevenly. Gravity pulled in all directions. Galaxies were expected to be misshapen, unstable, and chaotic. Order, in this view, was a late achievement, the result of billions of years of settling and interaction. James Webb tells a different story. Many early galaxies show signs of symmetry, rotational motion, centralized mass distributions. These features imply that gravity had already organized matter efficiently. Gas had time to settle into disks. Angular momentum had been redistributed. Internal structure had begun to stabilize. This is not what infancy is supposed to look like. Structure on cosmic scales is usually explained as the result of slow amplification. Tiny density fluctuations left over from the Big Bang grow over time. Under gravity, filaments form. Nodes emerge. Galaxies assemble at intersections. This process is gradual by design. Yet Webb reveals galaxies already embedded in organized environments. Early cosmic filaments appear well-defined. Matter flows seem established. The scaffolding of the cosmic web appears in place far sooner than expected. This suggests that the universe's initial conditions were more effective at producing order than previously believed. One explanation is that inflation, the rapid expansion thought to have occurred fractions of a second after the Big Bang, left behind density fluctuations that were more potent on small scales. Even slight changes in those initial conditions can dramatically affect how quickly structure forms later. Another possibility is that dark matter played a stronger organizing role early on. If dark matter clumped more efficiently or interacted differently at early times, it could accelerate the formation of stable structures. Dark matter halos define where galaxies form. If halos assembled early and densely, they would impose order quickly. Gas falling into these halos would inherit that structure, leading to organized galaxies from the start. There is also the influence of black holes. Massive central objects act as gravitational anchors. They stabilize orbits. They concentrate matter. If black holes existed early, they would accelerate internal organization within galaxies. This reinforces the idea that galaxies may not have slowly assembled and then developed centers. They may have formed around centers that already existed. The presence of chemical enrichment also contributes to organization. Metals enable efficient cooling. Cooled gas settles more easily into disks. Star formation becomes regulated rather than explosive. Order replaces chaos. James Webb's detection of metals in early galaxies implies that this transition happened quickly. The universe did not linger in a primitive state. It advanced rapidly toward complexity. This early organization challenges the assumption that time alone produces order. Instead, it suggests that the universe had a strong predisposition towards structure. Gravity, given sufficient density and minimal resistance, does not hesitate, it organizes. This realization has philosophical implications as well as scientific ones. We often imagine the universe beginning in chaos and gradually finding order. James Webb hints that order may have been embedded from the beginning, not perfect order, not uniformity, but a tendency towards structure that manifests as soon as conditions allow. This also affects how astronomers interpret irregularity. Some early galaxies do appear distorted or asymmetric, but these distortions often coexist with underlying organization. Chaos and order are not mutually exclusive. They can emerge together. The early universe may have been both violent and structured. Mergers occurred, shocks propagated, yet underlying gravitational frameworks persisted. This duality helps explain rapid evolution. Violent events drive change. Stable frameworks preserve structure. Together, they allow systems to grow quickly without dissolving. Another implication concerns timescales. If organization emerged early, then the processes that depend on it could begin sooner. Disk formation, star formation, regulation, black hole feeding, chemical recycling. This compresses the timeline for everything that follows. It also influences how we think about the future of cosmology. If early structure formation was more efficient than expected, models must account for that efficiency without breaking what we already understand. This may require refining dark matter properties, revisiting feedback assumptions, adjusting initial conditions. None of these changes are trivial, but all are necessary if theory is to match observation. James Webb has not given us a chaotic early universe struggling toward order. It has given us a universe that organized itself almost immediately. This does not mean the universe was calm. It was energetic, dynamic, violent. But within that violence, structure emerged and persisted. The early universe appears less like a random assembly and more like a system following an efficient blueprint. What that blueprint is remains unknown, but its effects are clear. Galaxies formed early and coherently. Black holes anchored structure. Stars enriched environments quickly. Matter flowed along established pathways. This is why the universe appears older than it should. Not because time moved faster, but because organization did. The universe did not wander toward structure. It moved directly toward it. And James Webb has shown us that the foundations of cosmic order were laid far earlier than anyone expected. As James Webb continued to peer into the distant universe, its discoveries were not limited to galaxies and black holes. It also began revealing something far closer to home in cosmic terms: planets. Worlds forming, evolving, and in some cases surviving conditions once thought to be unsurvivable. Exoplanets were already a well-established field before Webb. Thousands had been detected. Their sizes, orbits, and frequencies reshaped our understanding of planetary systems. But most of what we knew came from indirect methods: transits, radial velocities, shadows, and wobbles. James Webb brought something new: direct atmospheric insight. By analyzing starlight filtered through planetary atmospheres, Webb revealed the chemical composition of distant worlds with unprecedented precision. Water vapor, carbon dioxide, methane, clouds, hazes. Entire atmospheric profiles emerged from faint spectral fingerprints. What surprised astronomers was not just what Webb found, but where it found it. Some of the most intriguing discoveries involved gas giant planets orbiting stars that were already dead or dying, white dwarfs, stellar remnants, systems that should have been hostile to planetary survival. According to traditional models, when a star exhausts its fuel and expands into a red giant, it engulfs nearby planets. Tidal forces tear them apart. Radiation strips atmospheres, orbits destabilize. Survival is unlikely. Yet, James Webb observed gas giants that clearly endured this violent phase. This forces a revision of planetary resilience. One explanation is migration. Planets may not form where we see them today. Gas giants could form farther out and migrate inward later. If migration occurs after the star's most destructive phase, survival becomes possible. Another explanation involves mass and gravity. Gas giants are massive. Their gravity can help them retain atmospheres even under intense radiation. They are more resilient than smaller worlds. There is also the role of stellar mass loss. As stars lose mass during their death, planetary orbits expand. A planet that was once close may move outward. Escaping destruction, the system reorganizes. James Webb's observations suggest that planetary systems are more adaptable than expected. They can survive dramatic transformations and still persist. This has implications beyond individual planets. It reshapes how we think about planetary system lifetimes. Systems do not simply end when stars die. They evolve. This parallels what James Webb is revealing on cosmic scales. Galaxies survive mergers. Black holes survive recoil. Planets survive stellar death. The universe appears robust. These discoveries also intersect with the theme of rapid early growth. If galaxies formed early and stars enriched environments quickly, then the raw materials for planets may have existed earlier than assumed. Metals are required for planet formation, especially rocky planets. If metals appeared early, then planets could begin forming earlier. Gas giants may have formed alongside the first generations of stars. This does not mean habitable worlds existed early. Radiation levels were extreme, environments were unstable. But the processes leading to planet formation may have begun surprisingly soon.
James Webb's ability to study exoplanet atmospheres also offers insight into planetary formation mechanisms. Atmospheric composition reveals clues about where and how planets formed.
Ratios of elements indicate formation zones and migration histories. These data suggest diversity. Planetary systems do not follow a single template. Formation pathways vary widely. Some systems are stable, others are chaotic. Survival is not guaranteed, but it is possible. This diversity mirrors what we see in galaxies. Not all galaxies grow the same way. Not all black holes follow the same path. The universe favors multiple solutions. The discovery of planets surviving stellar death also forces us to reconsider the concept of cosmic endings. Stars die, galaxies merge, black holes wander, yet systems persist in altered forms. This resilience may be a fundamental property of cosmic evolution. For documentaries focused on the early universe, these planetary discoveries provide an important bridge. They connect the distant past to familiar concepts: stars, planets, survival. They remind us that cosmic history is not just about abstract structures. It is about systems that endure transformation. James Webb is revealing a universe that is not fragile. It is adaptable. This adaptability helps explain why the universe could grow up so fast. Systems that survive disruption can evolve rapidly. Those that collapse entirely cannot. If early galaxies and planetary systems were resilient, they could continue building complexity even under extreme conditions. This also affects how we think about life's potential timeline. If planetary systems can survive stellar death, then the windows for habitability may be broader than assumed. Life, if it emerges, may have more time than expected. This does not imply inevitability, but it expands possibility. James Webb's exoplanet discoveries do not directly explain early galaxy growth, but they reinforce a consistent theme. The universe is better at preserving structure than we thought. It forms systems quickly. It allows them to adapt. It carries them through extreme transitions. From galaxies to planets, the message is the same. Growth was rapid. Survival was common. And evolution did not wait for ideal conditions. It proceeded whenever physics allowed. The early universe was not only fast, it was resilient. And that resilience may be one of the keys to understanding why the universe appears older than it should. James Webb is not just showing us where planets exist, it is showing us how long systems can last. And that longevity, combined with early efficiency, paints a picture of a universe that wasted no time becoming complex. From the first galaxies to surviving planets, the universe learned quickly how to endure, and that lesson continues to shape everything we observe today. As James Webb continued to transform our understanding of galaxies, stars, black holes, and planets, a larger and more profound question began to take shape beneath all of these discoveries. What do these findings mean for life in the universe? Not life as we know it on Earth, but life as a cosmic possibility shaped by timing, chemistry, and environment. For decades, astrobiology rested on a cautious timeline. The universe needed time to mature. Stars had to live and die to create heavy elements. Galaxies had to settle into stable forms. Planets had to assemble from enriched material. Only then could life even begin to be possible. This implied patience, billions of years of preparation before biology could emerge anywhere. James Webb is compressing that timeline. The early universe now appears chemically active far sooner than expected. Stars formed early. Supernovae enriched space rapidly. Galaxies organized quickly. The raw ingredients for planets appeared earlier than models predicted. This does not mean life existed early, but it changes when life could have existed. Life requires more than elements. It requires stability, time, energy sources, protection from radiation. Early cosmic environments were extreme. Radiation levels were high. Galaxies were compact and violent. Black hole activity was intense. Yet James Webb's discoveries suggest that not all regions were uniformly hostile. The universe was not a single environment. It was a mosaic. Some regions may have been quieter. Some galaxies may have stabilized faster. Some planetary systems may have formed in sheltered zones. The early appearance of organized galaxies implies that stable stellar systems could exist sooner. Stability is crucial. Planets require consistent orbits. Stars require predictable output. Chemistry requires time. The detection of planets surviving stellar death further emphasizes resilience. Systems can endure dramatic transitions and remain intact. This resilience increases the range of environments where long-term processes could operate. Another important factor is metallicity. Life depends on complex chemistry: carbon, oxygen, nitrogen, phosphorus, all forged in stars. James Webb's detection of metals in early galaxies implies that the universe began its chemical enrichment program almost immediately. This means that the elemental prerequisites for life were available earlier than expected. There is also the question of time. Life on Earth emerged relatively quickly once conditions allowed. Within a few 100 million years of the planet cooling, life appeared. This suggests that biology may not require extreme patience, only opportunity. If opportunity existed earlier elsewhere, then life's cosmic timeline may be broader than assumed. This challenges a long-held intuition that life is a late phenomenon in cosmic history. James Webb suggests that the universe may have been ready for complexity earlier. However, readiness does not equal realization. The early universe was dangerous. Intense radiation from stars and black holes could strip atmospheres. Supernovae were frequent. Gamma-ray bursts may have been common. These factors could sterilize large regions of space. But again, the universe is not uniform. Radiation intensity drops with distance. Shielding occurs. Not every region is equally exposed. Even today, the universe contains deadly environments and calm ones. The early universe may have been similar, only more extreme. James Webb's findings also affect how we think about habitability over time. If galaxies and planetary systems formed early and survived, then life could have multiple windows, not just one narrow band in cosmic history. Life could emerge, be extinguished, and emerge again elsewhere. The universe's history may contain many attempts, not just one. This idea reframes the question of rarity. Life may not be rare because it is hard to start. It may be rare because it is hard to persist. James Webb's theme of resilience suggests persistence may be more common than expected. Another implication concerns intelligence. Intelligent life requires long-term stability, billions of years of uninterrupted evolution. If the early universe was too violent, intelligence may have been unlikely early on. But if some regions stabilized quickly and remained stable, intelligence becomes less constrained by cosmic age. This does not imply ancient civilizations. It implies that the universe may not need to wait as long as once thought to become biologically interesting. James Webb also changes how we think about the future. If early complexity was possible, then future complexity may be more common than expected. The universe appears efficient at building structure. That efficiency may apply to biology as well. This does not diminish the uniqueness of Earth. Conditions here are specific. History matters, chance matters, but it expands context. We are not latecomers to a universe that only recently became capable of hosting life. We may be participants in a universe that has been capable for a very long time. This perspective alters the emotional tone of cosmology. The universe feels less empty, less delayed, more alive with potential. It also influences how we interpret silence. The absence of detected signals from other civilizations is often framed as evidence of rarity, but silence may have many explanations: distance, timing, communication methods, extinction. James Webb does not answer these questions, but it shifts the baseline assumptions. A universe that grew up too fast may also have become biologically interesting too fast. This does not mean life is everywhere. It means the conditions for life may have existed in more places and at more times than we once allowed. Another subtle implication concerns planetary atmospheres. James Webb's ability to detect atmospheric composition shows that planets can retain complex atmospheres under a wide range of conditions. Atmospheres regulate climate. They protect surfaces. They enable chemistry. If atmospheres can survive stellar death, then they may also survive early cosmic turbulence in some cases. This again expands the window of habitability. None of this is proof. Science demands evidence. James Webb has not detected life. It has not detected biosignatures. Those discoveries may come later, or not at all. But what it has done is remove some of the reasons we assumed life must be rare. It has shown that complexity is not slow. It has shown that organization is not delayed. It has shown that resilience is common. These traits are prerequisites for life. The universe James Webb reveals is not one that waited patiently for billions of years to become interesting. It became interesting almost immediately. This realization does not answer the question of whether we are alone, but it reframes it. We are no longer asking whether life had enough time to emerge. We are asking whether life could survive. And James Webb's discoveries suggest that survival, like growth, may be more common than expected. The universe appears eager to build, eager to organize, eager to persist. Life, if it arises, would be participating in a universe already skilled at complexity. In that sense, life would not be an anomaly. It would be a continuation. James Webb has not shown us life beyond Earth, but it has shown us a universe that did not hesitate to create the conditions that make life possible, and that may be one of its most profound revelations. By this point, the implications of James Webb's discoveries could no longer be ignored. The question was no longer what did Webb see, but what does it mean for the foundations of cosmology? Are our models wrong, or are they simply incomplete? This distinction matters. A wrong model must be discarded. An incomplete model must be expanded. Most scientists now lean toward the second conclusion. The standard model of cosmology still explains the universe on large scales with remarkable accuracy. The cosmic microwave background, large-scale structure, expansion history. These pillars remain intact. What James Webb has exposed are the weak joints, the assumptions buried deep inside models of early galaxy formation, star formation efficiency, and black hole growth. Cosmological models rely on recipes, simplified rules that describe complex physics, how efficiently gas forms stars, how strongly feedback suppresses growth, how dark matter behaves on small scales. These recipes are calibrated using nearby galaxies where observations are easiest. The early universe may not follow those same rules. One possibility is that star formation efficiency was much higher in the early universe. Models often assume that only a small fraction of available gas turns into stars at any given time. James Webb suggests that this fraction may have been significantly larger under primordial conditions. Another possibility involves feedback. Modern galaxies are regulated by feedback from stars and black holes. This feedback limits growth, but in the early universe, feedback may have been less effective. Gas inflows were stronger, densities were higher, energy may have escaped more easily. If feedback was weaker relative to inflow, then rapid growth becomes natural. Dark matter is another area of uncertainty. The standard model assumes cold, collisionless dark matter. This works well on large scales. But on small scales, discrepancies have long existed. James Webb's observations intensify these tensions. If dark matter had slightly different properties early on, such as self-interaction or warmer behavior, it could alter how quickly halos form and how gas accumulates. Even small changes can produce large effects. There is also the role of initial conditions. Inflation sets the pattern of density fluctuations that seed structure. If those fluctuations had more power on small scales than assumed, early structure formation would accelerate. This would not require new physics, only refinements in inflationary models. Then there is the possibility that multiple effects combine: higher star formation efficiency, altered feedback, early black hole seeding, modified dark matter behavior. Together, they could produce the universe James Webb is revealing. This convergence of factors would explain why no single change solves the problem. The early universe may not need a revolution in physics, it may need a rebalancing. However, more radical ideas are also being discussed. Some scientists question whether our understanding of gravity itself is complete. Others explore modifications to dark energy behavior at early times. These ideas remain speculative, but they reflect the depth of the challenge. What makes this moment unusual is that theory is now chasing observation. For decades, models, guided expectations, telescopes filled in details, James Webb reversed that dynamic. Now, observation is leading, and theory must follow. This is not a failure of science. It is one of its most productive states. Periods when data outpaces theory often lead to breakthroughs, new frameworks, refined assumptions, and deeper understanding. The debate unfolding in cosmology today is careful, not chaotic. Scientists are not abandoning the standard model. They are interrogating it, testing its limits, identifying where it needs extension. This process will take years. Simulations must be rerun with new parameters. Alternative models must be tested against a growing body of data. Predictions must be made and falsified. James Webb will play a central role in this process. Its observations will continue. Deeper fields, larger samples, more detailed spectra. Each dataset will tighten constraints. Other observatories will join the effort. Future telescopes will complement Webb. Gravitational wave detectors will probe black hole mergers. Radio observatories will map hydrogen in the early universe. Together, these instruments will either confirm the emerging picture or reveal new surprises. One thing is already clear. The early universe was not a scaled-down version of the modern one. It was a distinct regime. Physics operated under different balances. Assumptions that hold today may not hold then. Recognizing this is a step forward, not backward. Cosmology is not being rewritten from scratch. It is being refined in the place where it matters most, the beginning. The question of whether our models are wrong or incomplete may ultimately resolve itself as both. Some assumptions will be discarded, others will be adjusted, new terms will be added. This is how science grows. James Webb has forced cosmology into a period of creative tension, a moment where certainty gives way to curiosity. The universe did not behave exactly as predicted, and that is precisely why this moment is so important, because it reminds us that nature is not obligated to follow our expectations. It follows its own rules, and our task is not to defend our models, but to align them with reality. James Webb has not broken cosmology. It has challenged it to become better, to look honestly at what the universe is showing us, to accept that the early universe may have been faster, more efficient, and more organized than we imagined, and to build a theory that can explain not only what we hope to see, but what is actually there. This is not the end of understanding. It is the beginning of a deeper one. The universe grew up too fast. Now, cosmology must grow with it. The story James Webb is telling us is far from finished. In many ways, it has only just begun. What we are witnessing now is not a conclusion, but a transition, a shift from speculation to observation, from assumption to evidence. The future of cosmic discovery is unfolding in real time. James Webb was designed for longevity. Its mission will span many years, possibly decades. Each observing cycle will push deeper, fainter, further back. The discoveries made so far represent only a fraction of its potential. Future observations will target even earlier epochs. Astronomers will search for the very first galaxies, the first stars, the boundary where light first emerged from darkness. Each detection will refine the timeline and test whether the patterns already seen persist. One of the most important goals is to build statistical certainty. Individual discoveries are powerful, but patterns change science. Larger samples of early galaxies will reveal whether rapid growth was universal or limited to specific environments. Spectroscopy will play a crucial role. By breaking light into its component wavelengths, James Webb can reconstruct star formation histories, ages, metallicities, gas dynamics. This will allow astronomers to determine not just what early galaxies looked like, but how they evolved over time. Black hole studies will deepen as well. More early quasars will be identified, their masses measured, their feeding rates estimated. This will help distinguish between competing growth scenarios. Stellar seeds, direct collapse, primordial origins. Gravitational wave astronomy will complement these efforts. Future detectors will probe mergers of massive black holes at high redshifts. These signals will provide independent evidence of early black hole populations and their growth pathways. Together, electromagnetic and gravitational observations will offer a more complete picture of the early universe. New telescopes will join the effort. Next-generation observatories will extend James Webb's reach. Larger mirrors, broader wavelength coverage, higher resolution. Each will build on Webb's foundation. Radio telescopes will map hydrogen during reionization. X-ray observatories will study early black hole activity. Ground-based telescopes will provide context and follow-up. Cosmology is entering an era of convergence. Multiple lines of evidence will intersect. Inconsistencies will be exposed. Explanations will be tested. This convergence will likely bring surprises. James Webb has already shown that the universe is willing to defy expectation. There is no reason to believe it will stop now. Some models will be confirmed, others will fail. New ideas will emerge. This is the natural progression of science. What makes this moment unique is its proximity to origins. Understanding the early universe is not just about the past. It defines everything that follows: galaxy, evolution, star formation, black hole growth, planet formation, even the potential for life. If the early universe grew up too fast, then the universe we inhabit today is the result of a rapid and efficient beginning. That efficiency may be a fundamental property of nature. This has implications beyond astronomy. It touches on philosophy, on how complexity arises, on whether order is inevitable or fragile. James Webb suggests that under the right conditions, order emerges quickly. This challenges narratives of gradualism. It suggests that some systems leap toward complexity rather than inch toward it. The universe may be one such system. This perspective changes how we view our place in cosmic history. We are not living in a universe that slowly figured itself out over billions of years. We are living in one that established its foundations early and refined them over time. The stars we see today are descendants of ancient processes that moved with urgency. The galaxies around us are matured versions of structures that formed quickly. The black holes at galactic centers may be survivors of early cosmic chaos. We are, in a sense, living inside the aftermath of a very fast beginning. James Webb has given us a new origin story, not one of hesitation, but of decisiveness. This story is still being written. Each new observation adds a paragraph, sometimes a correction, sometimes a revelation. What is certain is that cosmology will not return to its previous comfort. The early universe can no longer be treated as a blank canvas waiting patiently for structure. It was active, productive, efficient. The universe grew up too fast, and that speed shaped everything that followed. Future discoveries will clarify the mechanisms behind this growth. They will tell us whether it was driven by unusual physics, favorable conditions, or some combination of both. They may reveal limits we have not yet imagined, or they may show that nature is simply better at building complexity than we ever gave it credit for. Either way, James Webb has done more than extend our vision. It has changed our expectations, and that may be its greatest legacy. Because science advances not when answers are found, but when better questions are asked. James Webb has given us better questions about time, about growth, about origin, about inevitability. The early universe is no longer a distant mystery inferred from faint echoes. It is a place we are beginning to see directly. And what we see is a universe that did not wait. It built fast. And now we are finally catching up to its story.